Hey, I'm Ben Jordan. You know, I've been playing around a lot with this NB3000 and it is very cool. I've got to show you a few tricks with this thing. So today, I want to show you how you can get started with an FPGA system on chip design, and this thing makes it totally easy. Come and take a look at it. Don't have a lot of time to talk about all the stuff that's on this board. There's a lot of things here, but let me point out a few of the things that I particularly like, starting with these ultra bright surface mount RGB LEDs. You can't believe how bright these things are. They're amazing. This 2.4-inch TFT panel is also a touch screen. Infrared receiver on the top of that. This edition is using a massive Spartan 3AN 1400 device. I can fit a lot of logic, or quite a large system on this thing. Hey, and there's also a couple of megs of SRAM, high-speed SRAM, SDRAM, and some parallel flash. There's also some serial flash. There's a whole lot of user IOs, expandability, PWM outputs, MIDI, RS485, Ethernet, VGA, RS232, high quality or high definition audio codec. There's a lot of cool stuff here. Not to mention also slave and host USB ports, which we'll be using today. So what I want to show you today is how to get started by plugging this thing in, getting your license activated if you haven't done it already, and then we're going to use the TFT screen, the LEDs, and a standard USB keyboard. And you'll see just how easy it is to get a really cool application up and running very quickly. So let's get started.
First, plug in the NB3000 power adapter and switch it on. You should see a screensaver startup, which is the default design that runs on it. Next, plug in the USB cable between the host USB port and your PC. If you haven't already activated your license, Altium Designer will prompt you to activate using the license that's linked to your Nano board. In this case, I'll choose Yes to activate the license and create a brand new user account to go with it. I can do that by clicking the Register with Altium button. Then I'll fill out the form for setting up an account. Only the fields marked with red bars are necessary. Clicking the Register button submits the data, confirmed by this message. My new account password is sent to me in an email. Next, I'll log in with the new account and change my password. Now we're ready to rock. First, I'm going to build the FPGA hardware part of the design. I'll be using the Altium TSK3000 processor core, as you can see in this diagram, along with some internal and external memory for code and data. I'll also link out to the TFT panel, LEDs, and USB host controller. The NB3000 uses an ISP1760 USB hub from NXP. Because this device supports USB 2 high-speed transfers, it's connected to the system's memory bus directly, and the TSK3000 gains access to it as a memory-mapped peripheral. So to get started building the system, in Altium Designer I'll create a new FPGA project and add a new OpenBus system document. Here's where the bulk of the design resides. First, I'll place the TSK3000 processor from the OpenBus palette. Notice that it has separate I/O and memory buses due to its modified Harvard architecture. Next, I'll place two Wishbone bus interconnects, one for the I/O bus and one for the memory bus. The interconnects automatically take care of memory map address decoding, interrupt connections, and also multiplexing of data lines. Now I'll place the memories. In this case, I want to use the SRAM controller for connecting to the external SRAM, but I also need the shared memory controller for connecting to the USB host controller chip, which is on the Nanoboard 3000 shared memory bus. Now I need to put down the TFT controller, the LED controller, and the peripheral USB interrupt connection for the USB host controller. I can start joining all these pieces together by adding open bus ports here, 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 and here. Also, I need to connect both the TFT controller and the CPU to the SRAM controller, because it will be used for the video display buffer and for code. That's made possible by adding in the Wishbone arbiter right here. The arbiter is essentially an easy-to-use DMA controller. The port with the red number is the high priority port I'm going to connect to the TFT panel. As for the USB controller, that needs to be set up in the shared memory controller, so I'll double-click to set it up here. I'll check the boxes for asynchronous RAM and USB. The default settings for both are fine for this design. 1 MB of SRAM and 512K for the USB buffer. Now I'm ready to connect the rest of these IP cores. I'll move them around a little just to make things a bit more neat and tidy. And there's the completed wiring for the Open Bus document. Now I'll assign the interrupts from the peripherals to the host processor. In the Open Bus Signal Manager, I'll choose the Interrupts tab and then assign the USB interrupt to int1 and the TFT controller interrupt to int2. Next, I'll add a top-level schematic to the design, and this will be used for all the top-level connections out to the peripherals on the PCB. Each one has a predefined port component in the NB3000 port plugin library here. For this design, I'll be using the SRAM 0 and SRAM 1 components, the shared USB SRAM component, the TFT, board clock, test button, and LEDs. The next step is to add in a sheet symbol for connecting down to the Open Bus system. That's easily achieved by using the Create Sheet Symbol from Sheet or HDL command here. You can see it automatically adds all the necessary I/O signals. The final step in designing the FPGA hardware is to wire up the I/O port components to the sheet. This is done using harness connectors, and these can also be automatically generated. I'll place the ones I need using Place, Harness, Predefined Harness Connector. First, I need the WB Shared Mem Control, the VGA32 ILI 9320, and WB Mem Control SRAM 16 harnesses. I also need an inverter for the reset button and an I/O buffer for the TFT panel. I can get those from the FPGA generic library here. Now I've completed the wiring, I can build it and download it to the target FPGA in Devices View. In Devices View, you can see there's currently no process flow, but this will change once I configure the project. That's done by right-clicking on the NB3000 icon and choosing Configure FPGA Project, then choosing the project name. This step automatically builds the necessary constraint files for the design. Now, I'll kick off the FPGA build process. While that's running through synthesis and place and route, I'll get the embedded software project going. I'll start by creating a new embedded project. Then once I've saved the embedded project file, I can link it to the FPGA project, switching to Structure Editor view and dragging the embedded project over the TSK3000 icon. Now that the projects are linked, any information or changes to the hardware design will be propagated into the software design. And to show you what I mean, let's take a quick look at the embedded memory map. This came in directly from the hardware design automatically. Now we need to build the software platform that will make the C coding trivial. I'll add a new SW platform file to the project for this. I'll save it and click on the Import from FPGA button to bring in all the code wrappers for the peripherals used by my design. Now I can build these software API stacks up to the level of abstraction I need. I'll build the USB stacks up to the USB keyboard I/O context, the LED controller driver, and the text display context. I can access code from any of these drivers or contexts in my design, so I can write code to whatever level of abstraction I want to. To make C standard I/O use the USB keyboard and TFT text output, I can set up the generic I/O device down here. I'll assign standard in to the keyboard context and standard out to the text display context. And that means when I use printf, the text will come up on the TFT panel, and when I use scanf, it will take characters in from the keyboard. The final stage is to write our simple Hello World application and then compile and download the software to our target FPGA. I have some code set aside in a code snippet. All it has so far are the necessary includes for the software platform drivers, C library code, and a very simple main code loop that uses standard I/O put char and get char to perform local echo on the TFT panel when I type on the keyboard. Of course, I could use scanf or printf if I wanted to. Now all I need to do is click the Build and Download button, and the code is downloaded to the target and immediately begins execution. You can see the keystrokes going to the TFT screen here with the default font. But if you want to, you can generate your own fonts. So I already have a really useful system here, but there's more we can do since we added the LED controller. I'm going to paste in some updated code that takes simple commands from the keyboard to control the color of each of the LEDs. This code has been extended from before. I still have the same includes, but I've added a user prompt function as well as an LED brightness control function, plus I've extended the main program loop to pass the single key commands and set the LED colors accordingly. Building and downloading using the same button as before gets the new application running on the target. I think that's awesome. Not only did we get a system going super fast, but it can actually do something interesting and useful as well. Well, that's it from me this time, but make sure you check out the Nanoboard 3000 and the training videos in the training room, located on the web at nb3000.altium.com/intro.html. And stay tuned for more mini webinars on how to make the most of Altium Designer. I'm Ben Jordan and thanks for watching.